Okay, let's get started. Welcome to today's webinar on the future of AI in education and training. For those who are new to this webinar series, we organize them as a way to explore what impact AI can have on education, both in terms of how it can improve learning and how it can improve teaching, to help teachers to be able to teach more effectively. Today's speaker has done a lot of work in AI education and can speak to both of those points. He's going to be talking today about orchestration systems, systems which can help teachers help to orchestrate the activities, the flow of work and ideas within a classroom to help learning be more effective and help teachers to be able to focus on what they need to do in order to make the class be as successful as possible. So Kurt, welcome. We look forward to your talk.
Thank you, Louis. It's a pleasure to be able to speak with you today, even though I can't see you. As Louis mentioned, orchestration is all about what the teachers do with their classes when the classes get complicated. If a class has small group, individual, and whole class activities, then the teacher's management of that becomes complicated, especially when those activities share products like worksheets or ideas. An orchestration system is a computer system that helps the teacher and students get through such complicated lessons efficiently and with good learning gains. So since I'm going to be talking mostly about orchestration systems, it's worth a minute to see kind of where they fit in the overall space of educational technology. Then I'll get down into the details of what they actually do. That'll be a bit abstract, so I'll follow up with a specific orchestration system that's under development in my lab. Then we'll go back up to the abstraction level, summarize and point out a few points, and talk about future work. All right, so here is a graphic that has helped my students at least, and I hope it will help you sort of see the big picture. Orchestration systems are a kind of activity, and we'll talk about the technological supports for different kinds of activities. So let's first talk about lots of different kinds of activities. Of course, you can subdivide infinitely, but a pretty decent division is to subdivide into these 7 kinds of activities. These are things that students do. They can either be passive by reading or watching a lecture or video. They can be selecting answers like multiple choice questions or drag and drop or something. They can be building a large product, developing a large product like an essay or a computer program. They could be engaged in practicing a long process like medical diagnosis or negotiating a deal. Or they could be doing any of those things, but in a small group, like a pair or 3 or 4 people. That's group work. Lastly, we have classroom orchestration, which is where the students engage in any of the above activities in combination of both individual group and whole class work. And the teacher's role there is to guide the flow of ideas. Okay? Now, I've deliberately chosen and ordered those in such a way that they correspond with Michelin Chi's ICAP Framework, which is an acronym for interactive, constructive, active, and passive. According to her framework, as you proceed from passive through active, constructive, and interactive, learning gets deeper. So if all you need is passive learning, like vocabulary learning in a foreign language, then passive activities like might suffice. Selecting answers would be slightly better, but it doesn't do you much good to go higher. Going higher, well, in this case, lower in the list brings you deeper learning. Now we'll talk about the technological support dimension of this space. What I mean by that is tools versus assessments versus tutors. So a tool is a system that has no expectations about the student's performance. So when you're using a word processor, it doesn't know what you're trying to do with it. When you're using a forum, for example, it doesn't know what the student's roles are, tasks are, or anything. Those are all tools. An assessment is something that compares the student's performance to an expected performance. And it doesn't do very much with it. It might give like red-green feedback or compute a score, and it might show it to the student or the teacher, but it does at least compare the student's performance to an expected performance. A tutor, according to my definition, not only compares the student's performance to an expected performance, but it uses that to drive some kind of instructional policy. And that policy determines when it might give feedback, or more likely hints, when it would advance students to the next module, or what task to assign, or anything else. All those decisions are driven by a policy, which is hopefully an intelligent policy driven by experience. Okay, so what would we expect different technological support to cause in the classroom or at home? Well, of course, it depends upon whether there's a teacher there. If there's no teacher there, then you would expect good students to have basically do fine with tools and fine with assessments and fine with tutors, because good students are the ones who can learn from anything. I'm sure you've seen that. Poor students, though, need more help. So tools don't give too much help. So those students' learning gains would be less than if they got assessments, and even less than if they had a good instructional policy to help them. So you expect to see what's called an aptitude treatment interaction when these technologies are compared across with each other and there's no teacher. But on the other hand, if there is a teacher, then a good teacher will compensate for the tool's inadequacies. So that means that all the students will get about the same learning gains, but the load on the teacher will be much higher when the tool does with tools than with assessments versus tutors, because tutors take over more of the instructional work. Okay, but of course you have to control for everything, and that's hard, I know. So here's the big picture one more time. As you proceed downwards in the rows, you should be getting deeper learning through as you increase the complexity of the activity from passive all the way up to orchestration. As you move rightward in the columns, you should either see more learning if there's no teacher involved, or the same amount of learning but less teacher load as you move from tool to assessment to tutoring system. So that suggests that cell 18, the technologies in that cell, are a very interesting place to do research, and in fact, not very much research has been done there yet, as I will explain later. So just to sort of tie down how this space is populated, let's first look at what kinds of things a typical learning management system or a MOOC platform might have. They almost all have videos and text, and those are passive tools. They almost all have quizzes of some kind or another, and that's an assessment based upon selecting answers. Sometimes they allow you to submit files and essays, but they don't grade them, so they're just a tool in that respect. They often have forums or wikis or chats or other forms of supporting group work, and those are tools because they don't understand what the student's expected performance is. Now, in contrast, there's a bunch of other stuff that's been developed in our community and others that provide more support. Uh-oh, forgot to turn my phone off. One moment, please.
I guess professors need orchestration tools too.
Yeah, I know. I gotta work on that. Okay, so the tutors can do adaptive question selection when the questions are selecting answers. We see a lot of those. Alex, for example, is one. Automated essay scoring is just coming into play, so some systems are starting to use that in the real world, but it's been developed in labs for quite a while. Simulation-based training, both with individuals and group work, is widely available and often used, but not so much inside universities and K-12. Step-based tutoring systems are ones that monitor a long process of solving a problem or doing some other piece of work, where the work that what the person is doing can be broken into steps, typically, user actions on an interface, and then the tutoring system can strategically give help on those steps as the person works through their problem. So those are sometimes called intelligent tutoring systems. So a bunch of systems from my lab. Turns out you can assess passive activities, but you have to use strange sensors like eye tracking or fMRI. We have a very nice organic chemistry system, but all it does is adaptive selection of problems. A couple step-based tutoring systems. But the thing I want to spend most of my time talking about today, in fact, all of my time, is a system called FACT, which I'll introduce in just a few minutes. And that's an orchestration system. Now, I've told you sort of where orchestration systems fit. They're sort of in the last row of that table. Let's talk about what they do. I'm again going to use a different table, but the same columns. I'm going to talk about the features that orchestration systems has and divide those into tool features, which don't depend on any kind of expectation about what the student is going to do. Those that need that expectation, and then tutoring features where a policy is involved as well, an instructional policy. Now, the first 4 rows are all what you might call dashboard features. Those are things that appear on the teacher's dashboard or buttons on the teacher's dashboard. And the last row is stuff that appears on the student's screen without input from the teacher. So let's go over some of these. Now, this will just be a kind of abstract advanced organizer. I'm not going to really explain these features. I'm going to spend the rest of the time in this webinar talking about what those features are. So now I'm just sort of giving you a list to begin with. So let's briefly define each of these things. So a lot of orchestration systems have a pause button, which causes all the student apps to freeze up and show something like eyes on teacher or pay attention to teacher. The project button causes something on the teacher's dashboard to appear on the digital projector in the classroom. The peek button allows the teacher to look at a student's screen. Advance is a button that causes the whole class to transition from the current activity to the next activity in the lesson plan. Off alerts tell the teacher when a student has gone off task or offline. So those are used in all kinds of activities. For activities that are used mostly in whole class settings, one that's occasionally found is a button which the students press to indicate that they find the current topic or slide in a PowerPoint presentation muddy. They don't understand it. Polling, that's widely used with clickers. That's where you ask the class a question, multiple choice, students select their answer, it appears on slides. Now, when you're working with groups, you need some tool to control the membership of the groups, to keep the machine apprised of who's in which group. When working with either groups or individuals, software often gives students a help button so they can raise their hand and ask for help without actually raising their hand, a sort of covert way of getting help. Similarly, the students can indicate by pressing a done button whether or not they're finished. Tools often record the student's performance and allow the teacher to send messages to the whole class or to individual students. So those are ones that don't require any knowledge of or expectation about what the student's performance will be. Those which require such a thing monitor either participation, which means, how is a group working together or failing to work together. In the group or individual setting, we have a bunch of comparisons to the students' sort of progress through the problem-solving exercise, their errors, whether they have any or not, and something which aggregates over all the students in the classroom and shows the teacher which errors are currently the most common in the class. Down on the bottom row, sometimes some of that information is shown directly to the students, either as flags on the errors or indicators, nags about participation, stuff like you need to take turns. Now, intelligent tutoring systems and computer-supported collaborative learning systems often have interesting policies that talk about participation in the case of CSCL systems, or errors or individual advancement in the case of ITSs. Orchestration systems have recommendations to the teacher appearing on the dashboard for who to call on in a group setting, in a whole class setting, which people should be in what kind of groups. They also have recommendations in both group and individual activities for which students to visit, whether to pause the class, whether to advance the class, and what to project onto the screens. So that's a brief overview of a whole bunch of features. Let's go take a look at FACT as an illustration of what some of these features are, okay? So FACT was originally designed around this research question. Can it help a class that's doing the classroom challenges? So here's a British class that's doing the classroom challenges. What are the classroom challenges? Okay. They were developed over a 10-year period by Alan Schoenfeld, Hugh Burkhart, the late Malcolm Swan, David Foster, and a whole host of other folks. There's approximately 100 of them available. They're for grades 6 through 10. They're all about math. And in a large RCT, randomized controlled trial, it had a 6.6 effect size. In other words, a whole half a year of math instruction just by using these things during 1 year. So very effective instruction. As not too surprisingly, they're very widely used. There's been over 7 million downloads of the PDFs and PowerPoints, and they're very often used for professional development. They're exemplary lessons. Unfortunately, nobody knows about them except math teachers. So if you'd like to learn about them, go to the website. Now here's an example of one classroom challenge. So the students are given that bunch of cards down at the lower left that say money cards. They're just given 4, and they put them in the corners of a big sheet of paper, a poster. And then they're also cut out a bunch of arrow cards from a piece of paper. And those look like that one at the bottom there. It says up by 25%. And their job is to arrange the arrow cards so that they represent the mathematical relationship between the money cards. And you see at the upper right there the correct placement of these cards. But of course, they don't know. That's just, they don't know that. They're never shown that. What they do is first work individually placing the arrow cards, and then they take their individual work and show it to other people in a group, and then the group decides what their best answer would be by combining the individual answers. And then teachers show individual group work to the whole class and ask for criticism. And throughout this whole process, the teacher's role is not to give feedback. In fact, the students never get feedback on this activity. Instead, it's sort of like survival of the fittest. Hopefully the best ideas will percolate upward from individuals through small groups to the whole class. To encourage that to happen, after they've placed the percentage cards, then they place some decimal cards, first as individuals, then as small groups, then as a whole class. And finally, they place fraction cards. That's usually when the light dawns, because then they see that a proper placement involves just inverting the fraction. So this whole classroom challenge is designed like a big funnel, so that students make a lot of mistakes at the beginning and then gradually funnel in on the correct concept. And all this is done without any feedback from the teacher. Okay, and this type of instruction is sometimes called formative assessment-based instruction. It has many other names too. Mercer and other people develop stuff. Here's some classroom challenges that are a little different. On the right, we see students who are pairing a story with a distance time graph. On the left, we see students who are figuring out how to develop a sampling procedure so that they don't have to count all those little dots and triangles. Here's a classroom challenge lesson in action. The students have big sheets of paper. They've got calculators, they've got scissors, pencils, and most importantly, they have glue sticks to make sure those things stay stuck down. The teacher is occasionally holding up a poster and having the class discuss it. And that's what a classroom challenge is like. Now, the FACT system was developed to support the classroom challenges. It was a big project funded by the Gates Foundation and more recently by NSF. It involved a team of people both at Nottingham, Berkeley, and SVMI. Those are our instructional developers, designers, and then a bunch of system developers here at ASU. So here's students working on FACT. These two students are in a small group, just 2 people, and they're solving a problem together. They each have their own tablet. One of the principles of FACT is everybody gets their own device. That means that they work sort of face down, even though they're right next to each other. These students are talking to each other quite a bit, even though they're face down over the tablet. What they're looking at is a digital version of the paper materials. So this is a close-up of a part of a poster. The poster is from that I showed you earlier. This is stories being paired with distance time graphs. The stories are on cards, and so are the distance time graphs. And the students can move those so they're next to each other. They can also add more cards to the poster, and they can write. They can write with a stylus, or they can write with, oh, I haven't got to that yet. They can pinch and scroll and zoom because it's a big poster being seen on a small screen. Now I get to say that they can draw with their finger or a stylus or a mouse, and they can type. When they get done with this activity, they can press the done button, which turns a signal on in the teacher's dashboard. The teacher carries that dashboard around the classroom on a small tablet, and the teacher then, typically either by visiting a student or by seeing that the student needs help on the dashboard, comes over and talks with the student about their work. Okay, so this is a pair of students who are being talked to by one of the teachers. So what does the teacher's dashboard look like? It has a tile for each student in the classroom. So this classroom has just 5 super students. Batman and Robin are in the same group. We can tell that because they have 1. That's group 1. Group 2 has Catman and Spidey in it. All the tiles after the students get started have a progress bar. So Catwoman and Spidey have gotten going, but Batman and Robin haven't started yet. Tiles turn gray when Fact's heartbeat stops, which it does when the student goes to check Facebook or their machine runs out of battery. So how does the student control their class? Well, to start with, when the students sit down and they get their tablet started and they go to Fact, which is a web app, they type in this class code. That's a lot easier than dealing with the school's IT department and authentication codes and stuff. Then this teacher chooses one of the classroom challenges, chooses an activity or just presses the next button, and that causes a set of posters for that particular activity to become available, which the teacher can access from the poster button. Typically, an activity comes with a launch poster, which explains the rules for doing the activity. Teacher can choose to project it by projecting anything, in fact, that appears on their dashboard by pressing this project button. And that causes it to appear on the screen so the students can see it. When the teacher's in the middle of a class and wants the students to pay attention to her for a few moments, she can press the pause button, which causes the Fact apps all around the classroom to freeze up and display eyes on teachers. And every time I've observed a class, all the students groan simultaneously as soon as they see that eyes on teacher. But they do pay attention, so it's like a 10-second transition, as opposed to the normal one where the teacher is class, 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 please stop working, I want to talk to you. It's a lot more efficient. So, design issues. We learned a lot by building the Fact system, and I think anybody would building their own orchestration system. So we've run into about 42 design issues in the 52 classroom trials that we've done so far. 20 of those turned out to have simple solutions. 10 required very complicated pieces of software development, and 12 we haven't solved yet. So just to give you a flavor of what we've learned, I'll talk about one simply solved issue and one complexly solved issue. So here's a simple one. When the students file into a classroom, typically the teacher has already decided how to group them and tells them where to sit. Often it's the same place every day, so they're always in the same groups. But unfortunately, the orchestration system can't see who's seated where. So how do we get it to know? Well, one way is to have the teacher input all those groups, perhaps by having taking a photograph of the seat map and having the system parse it. Alternatively, we could have a vision system recognize the students' faces. That's a little dicey. An indoor positioning system that recognizes the students' devices might work, but we haven't tried it. What we did instead was just put it all in the hands of the students. So as soon as the teacher pushes the join group activity, the students see on their tablet this huge menu, which just lists the group numbers. Then meanwhile, the teacher is projecting the what you see there, the tiles, and the students can see what group they're assigned to and who else is assigned to that group. So they press a group number pretty much at random, and then if only their group members are in that group, everything's fine. But if there's somebody in their group who's not supposed to be in their group, they yell at them and say, Charles, get out of group 4. We're group 4. You got to be some other group. And that process, which is a lot of fun for the students, takes maybe 30 or 40 seconds. It's not a big deal. And it's a lot easier than having the teacher manually put all the students in the group. So we're very happy with that. We didn't discover that until about trial 30. A complex design issue, formative assessment. This really requires a lot of software. So when a teacher visits a classroom challenge group or student, the teacher usually stands behind them for a while and then eventually might ask, "How are you doing?" Then the teacher has only a few seconds to understand the poster, which is sort of far away, and they might have to lean over to see it. And then they can finally, in just a brief few seconds, come up with something substantive to say to the students. So this analysis of the poster is often called formative assessment because it's determining what kind of instructional move the teacher should make. The teacher doesn't use it to score the poster. They're using it to decide what to say that might help the students learn more. Unfortunately, formative assessment is a huge cognitive load for the teacher. And our question was, could we have fact relieve them of part of that load? So to give you an idea what they face, this is a poster that was submitted for one of our tasks. You can see it's very complicated. The different colors correspond to different students. Okay, we give each student a different color. Here's another poster and yet another one. And oftentimes they've got interesting doodles, sometimes love notes, all kinds of stuff. So what we have to do is parse all that. So to do that, we associate a set of detectors with each poster. And a detector is designed to match some of the writing or card arrangements on the poster. And if it does match, then it posts an alert. The alerts stick with the poster, and only when the poster changes so that the detector is no longer valid, only then does the alert go away. Now, how the detection occurs depends very much upon what it's trying to detect. So we look at whether ink strokes, text, or card arrangements. So for ink strokes, fact heuristically segments it into handwriting, graphs, tables, and doodles. We use MyScript to convert the handwriting to text, and unfortunately, we haven't got around to doing anything with the graphs, the tables, and the doodles. We're working on a doodle detector. That's another form of off-task behavior. Good, sometimes not a bad thing. Once we have some text either typed in from the student or generated via MyScript from handwriting, then we parse it by looking for keywords and by trying it to parse it as math, because it could be a math expression. Whichever one matches the best, keywords or math, then we give it that interpretation. Other information is conveyed by the position of the cards on the table, like those arrow cards that we saw earlier. Their relationship to the money cards determines what the students are trying to say. Okay, so to parse that, we have detectors that are simply associated with every possible pairing of cards. There's a finite number. It's a large, but there's a finite number. Once alerts have been posted, the teacher can see what they are by peeking at a student's poster. So to peek at a poster, the teacher taps on one of the tiles. So this teacher has tapped on Catwoman's tile and is now peeking at Catwoman's poster. Fact is smart about where the alerts appeared, so it'll scroll and zoom so that the alerts occupy the center of the window. The alerts basically are associated with a particular piece of the student's work, and that piece of work has got a red rectangle around it. So there are two alerts showing here. And if the teacher is a good teacher and is very familiar with these materials, just showing them what needs attention is sufficient. They look at it and instantly know, oh, I know, I've seen this a zillion times. I know exactly how to talk to the students about this. However, if that doesn't work, then the teacher can tap on the exclamation point, and then what they see is this sidebar popping up. This allows the teacher to see scroll one by one through all the alerts. When they're looking at a particular alert, they first get a description of what it is. We use the word misconceptions for these things. It's not exactly right, but they get a verbal, sort of an expositional description and some examples. But most importantly, it gives them a message that our instructional designers think would be good for teachers to present to students. They often use this as a lead-in in a conversation, but on the occasion when the teacher is peeking at a group and sees this alert, and that group is a high-functioning group with students who are very good at accepting advice, then the teacher might just want to send this message straight to that group, and they'll probably do good things with it. So in that case, of course, they press the send button. On the other hand, if the teacher doesn't like this recommendation, then the teacher, we ask them to press the delete button, and that records it, so our analytics will tell us to come look at that and see what's wrong. Okay, they can also just cancel this and go back to peaking. So that's how we handled formative assessment. And what we hoped was it would allow teachers to more rapidly start talking to students. And in fact, by using videos, we determined that that was true. So on the right, we see a big orange fraction of visits that were preceded by this teachers standing behind the students for quite a while. And then they finally started talking. On the left is, we could see that the orange segment has gotten very small, because when the teachers walk over there, they're looking at the alert, and as soon as they get there, they're ready to talk. So that saves time for the teachers. We also found out that the conversation that occurs often has more specific content when the teachers first view an alert. So when alerts were turned off, they would also often go up to the students, look at the poster, and then say something general like, don't forget to take turns, or be sure to explain things to your partner. So that's a case where no specific content was discussed. We would prefer them to say something more specific, like, think about what would happen if Tom walked in a circle around his house. And if they do think about that, that will encourage them to sort of proceed further down the funnel and discover the right concept in the classroom challenge. So we want that specific content. We're seeing that we're getting more of it with the alerts. I wish we had even larger blue segment here. So now the reason for presenting fact, besides just to brag, was to illustrate some orchestration features. So let's go back and see what some of those are. So you saw the pause button in the upper right, and you heard about how the students groan when the teacher presses it, because it causes their tablets to freeze and forces them to look at the teacher. Project button is handy for all kinds of reasons. We use it for joining groups. We use it for projecting launch posters. We use it for projecting student posters so the class can talk about them. By the way, that is a huge time saver. When the teachers hold up a paper poster, the cards almost always fall off of it, and that creates a disaster. So by having them project a poster digitally saves a lot of time and hassle. Peeking is when the teacher can tap on a tile and see the student's poster from across the room. And we noticed, by the way, that teachers often do that and then say something to the students across the room like, good job, group 5. And group 5 sees the teacher's not anywhere close and says, uh-oh, we're being observed. So this is an effect which Ken Holstein and Ido Roll have dubbed the policing effect. So we get that. They can tap on the advance button, which causes the students to progress from one activity to another. And in the classroom challenges, that's a big time saver, because what happens if you don't have it? Well, you have to collect all that paper and then hand out a bunch of new paper. And then they have to cut the arrows and stuff out of a piece of paper, and that all takes minutes. So by just pressing a button, the advancement from one activity to the next is instantaneous. We've got the tiles turn gray when the students go off task or their tablet goes offline. So we already talked about the join group activities down there in the group row, so I'm talking about this membership tool feature. So orchestration systems need some way to know about the membership in groups, and we found a way to do that nicely. Moving down vertically, we don't currently have a help button, but hopefully by the end of this sprint, we will have one. We do have a done button. The help button would be pressed when a student wants the teacher to come over, talk to them, but doesn't want to raise their hand. So they want to anonymously ask for help. The done button is pressed by students when they are just getting finished with an activity, and it causes the tile to turn green, alerting the teacher to, that group needs something new to do because they've run out of work. Or at least they think they have. They may not, but they think they have. We record all the students' activity in a giant log file. The teachers can then take home fact, and at home they can connect to the net and replay any student or group's work, which is useful for diagnosing their own teaching issues, as well as for formulating what to do the next day. The teachers can press a button that sends a message either to the whole class, like 5 minutes left, or to an individual student, like stop messing around with Facebook. So those are handy, but not actually used very much because they require typing, which is slow. In the middle column, assessment features, we currently have a set of participation detectors, which, unlike the detectors I was talking about earlier, these look at the log file rather than the poster, or I should say the log stream rather than the poster. They're looking for sequences of actions in a group that indicate that that group is not participating as they're expected to be. So if this is an activity where they're supposed to show their individual posters to the whole group and then finally start working in the group poster, if that doesn't happen, which we can detect from the log stream, then a participation detector fires and posts an alert on the dashboard for the teacher. If the students are supposed to be taking turns and they're not, then a participation alert goes up. However, the most important participation detector is also the most difficult one, and that's one which triggers when the students are not collaborating appropriately. So they may be taking turns, but if they're not explaining to each other what they're doing, then they're not collaborating appropriately. So that detector is the hardest one, and it's still under development. Moving downward to the group and individuals, I think I showed you briefly the progress bars at the top of each tile that indicate how far students are along in their work. The progress bar has got a portion that's red, indicating the number of incorrect actions, and a portion that's green, indicating the number of correct actions. Errors are what we call alerts, and you can see, the teacher can see those by peeking at students. I forgot to mention that the bar is red on a tile if there are alerts pending for that tile and blue otherwise. So the teacher can see from the dashboard who's got alerts. The teacher can also see at the very bottom a list of the errors that are common in the classroom. So 50% of the students have exactly the same error. That'll show up in a table at the bottom of the dashboard. Teacher might want to pause the class and address that particular error to everybody, a discussion of that error to everybody. So finally, down in the bottom row, we're just starting to send alerts directly to the students without sending them through the teacher first. And one of them is participation alerts. So like taking turns, if they're not taking turns, that alert will go straight out to the students, but only after the students have been working for 5 minutes. We kind of want them to get settled in on a task before they start getting such alerts. On the right hand, we're beginning to develop policies which turn our system from an assessment system into a tutoring system. Currently, we have policies for recommending whom to visit. Now, this comes out by essentially causing only some of the tiles to turn red on the dashboard, indicating the alert is pending. Initially, we turned every tile red that had an alert pending, which meant that after a few minutes, every tile on the dashboard was red. So the teachers basically said, this is worthless. Just show us the important ones. And we've been struggling with that ever since because we don't know what's important. That's an instructional policy issue. So we've been working with our teachers. We've tried 3 policies so far. They're happier with the last one than any other one, but there's still room for improvement. That's why that's a kind of lighter shade. We don't think our solution is anywhere close to the adequate solution. Same thing with deciding about which participation alerts to send to students and which poster alerts to send to students. We're doing it now, but we're not confident that the instructional policies that we've developed is correct. Okay, so that's a brief tour of the features of all orchestration systems illustrated by the features effect. So back to the abstract level, orchestration systems in general. So it turns out, there's been a lot of orchestration system development work in the last 10 years or so, and they fall into 3 groups. Those which are already out there being used, and those are called classroom management systems. A bunch that were developed by people who are basically interested in computer-supported collaborative learning, the CSCL community, and a bunch that are being developed on top of intelligent tutoring systems. So let me go through each of those. So the classroom management group only has tools. They got those ones you see listed there: pause, project, peek, advance, off alerts, polling, help button, record, and messages. Down at the bottom are 3 very popular classroom management systems. These things intervene with the students' tablets or laptops at the operating system level. So they don't know anything about the apps that are being run on those tablets, but then nonetheless, they can provide all these advantages. So the good thing about them is they're general. You can use them with any piece of software that you've been using with your students and have these additional advantages. The bad thing is that they can't possibly do assessment or tutoring because they have no way of accessing the data structures inside the apps that are running on top of them. So CSCL, intelligent tutoring systems, often these days people put on a dashboard, converting them from a pure intelligent tutoring system to one that's an orchestration system. People like to put, and very often put, progress bars, alerts for errors, and sometimes put a table of common errors on the teacher's dashboard. Occasionally you see dashboards that have a peek capability as well, so that the teacher's dashboard can display whatever the student's working on right now. Of course, as an intelligent tutoring system, it still shows error flags to students or advances them individually, or in some cases has good policies for hints and so forth. So one of my favorite ones is the Lumillo, which was an orchestration system developed at CMU by Ken Holstein and his advisor Vincent Levin and Bruce McLaren. What makes it interesting is instead of using a dashboard to present, instead of presenting the dashboard on a tablet or a laptop, it's presented in augmented reality goggles. So when the teacher looks around the classroom through the goggles, instead of seeing alerts on a dashboard, the teacher sees icons appearing above the heads of the students. So very interesting HCI issues there. Okay. As an example of the group of orchestration systems that are derived from CSCL systems, Argonaut is a great case. Argonaut basically is the students are building arguments in a shared workspace and then conversing in a typed chat window. So this is real common for CSCL systems. There's a workspace and a chat window. They have a chat window so that the system can understand what the students are saying to each other without having to deal with speech. So Argonaut uses tag helpers and more recently some other text processing things to determine whether the contributions to the chat window are sort of on topic and transacted. Mainly they follow from each other. One participant's comment follows from earlier participants' comments. Of course, it has to have some way of knowing who's in the group. It records the sessions and allows the moderators to send messages to the students. So there's several systems in this category. So I've talked about the three categories, but what we really need is more work on policies. And the reason for that is that these dashboard-laden systems are getting pretty good at providing teachers with sort of a heads up or awareness of the state of their class. Typically, that means that they're going to see a lot of alerts pending. They're going to see a lot of progress bars, which are not where they want, and yet they. Oh, my other phone is ringing. Let's just hang up on that person. That means that they're aware of lots of issues that need their attention, but there's only one teacher. So, excuse me. So there's only one teacher. So what the teacher really needs is recommendations for which of these things that they can do is the most important. And they need some way to control a policy which puts the system in a position to send something to take care of each of these issues by itself. So we wanted to send alerts, sort of messages about participation, about errors that allow to advance students individually. Down in that lower right corner, that's going to be absolutely key in the future. Of course, to provide recommendations for what's important, what the teacher should do, we have to have instructional policies for that. And that, I mean, there's a lot of work in the teaching community about that, but it's sort of more theoretical. We need it down at the lower level of what do I do now in this situation? We might be able to machine learn that, but the data you require for that is like amazing. I mean, how are you going to get enough classrooms to figure this out? And what does it mean to be, what is a measure of success for classroom interaction? So we have a lot of big challenges awaiting us here, but they're really important because teachers desperately need this kind of help. The This is probably why there isn't very much technology in the classroom. It's because it's not helping the way it should help, and I think this would do that. So thank you very much. I appreciate your attention, and it's time for questions.
Absolutely. Well, thanks a lot for that great talk. Reminder, if you have questions, type them into the chat window, and I'll be monitoring those and make sure that Kurt answers them. Also, if you want to see additional papers about Kurt's work, follow the link on the screen there, and you'll find interesting and relevant publications. So I've got a few questions here to sort of kick things off. Could you tell us a bit more about how teachers were involved in the design and evaluation of FACT?
Sure. As I mentioned, there were 52 classroom trials. Each of those trials was with a teacher who was already an expert in using the paper-based versions of the classroom challenges. So that teacher really had a strong idea of how class should be conducted and what they wanted their classes to do. And so when we put FACT in there, they had strong ideas about how it was helping or hurting them. Instead of like doing an interview afterwards, we had them talk to us during class, and they were expert teachers, so that wasn't a problem for them. So each one of these trials then involved the teachers teaching and also interacting with the experimenter, who generally stood right next to the teacher, followed them around. So that kind of, and then also we had, courtesy of Silicon Valley Mathematics, a couple of observers in the classroom. And these are trained observers who had helped develop classroom challenges, and they knew how to talk to students. So they would go around and ask questions to students. So we basically had a whole team composed of researchers, observers, teachers, and students who were all focused on getting the classroom challenges to work good in this technological environment. That kind of thing, that co-design process is sometimes called a design-based research, but we didn't know that. We just did it. We're a bunch of engineers. So, and it works great up to a point. And we're at that point now, which is now we are improving things, we think, but we don't have any measures to tell us whether it's a sort of a big change or a little change, it's worth doing or it's not worth doing. So we're now at the point where we have to have a more metric analysis of the goodness of the classroom processes, and we're working on that now.
Great. So this system was designed to support the classroom challenges, but I'm curious about how this could be extended beyond the classroom challenges, or what aspects of it are specific to the classroom challenge, classroom activity model, if you will.
Okay. Let's see. As you saw, a classroom challenge consists of a whole bunch of posters that students do and some posters that the teacher shows to students. So it's all about posters. And a poster is just a big graphic and has cards on it, which are also graphics. So as far as FACT knows, it's all graphics. That's the only instructional material. So if all you want to do is use the tool, FACT as a tool, then you just provide new graphics, and they don't have to be English, they could be Chinese or whatever. But if you want to use the expected performance features, the assessment tools, the tutoring tools, then FACT has to know something about the content of those materials. So this is not a model tracing system at all. It's not any of the common ITSs. It's what you might call a detector-based system. So all it needs is a set of detectors which can detect issues that are worth talking about to the students. And so we decided a long time ago that since example tracing tutoring systems seem to be working so well, we would build material-specific detectors. And so it turns out that, so each poster has its own detectors, and if you wanted to have detectors on your poster, you'd have to write them yourself. However, the process detectors, like taking turns and so forth, those are general. They could apply to any poster because they just look at log file actions. So we're getting some generality, but not as much as one would ideally like. So to answer your question in more briefly, you would have to develop new passive materials, posters. You would have to develop new detectors, and you would have to tune up the process detectors. That's what you would need to do to get a high functioning lesson.
Great. So a follow-up of the early question about relating to the design process. So how frequently do you engage in design classroom test revision cycles with FACT?
Let's see, we typically take FACT, we fly out to the schools, we do 2 days of work in the schools. Typically we do 4 classrooms, which have to meet 2 days because that's how long it takes to do a classroom challenge. Then we get all these comments from our teachers and our log files, and we take them all home and we code like crazy to take care of the problems. We follow up with our observers and our teachers over that time by email to clarify things. We talk to our colleagues in Britain and Berkeley. We often have focus sessions with them to fly new ideas by them because they're all developers and teachers themselves, designers and teachers themselves. And that process takes at least 3 months, sometimes a little longer. So we've generally been doing about, sometimes about 4, but sometimes only 3 class visits per year. And that's to the California site. The British site is on its own cycle. It also does about 3 a year. But since we don't fly to Britain for these, we have our colleagues there take care of it. We get data sort of in the off cycles from them. So it's been a very intense process over the years.
Great. Are you doing anything with audio detectors in addition to detecting what's going on with the posters?
Yeah, we are. The difficulty with detecting really good collaboration is that it happens by speech. So we've investigated using audio in laboratory settings by having students in the lab, not a classroom. 2 students are working in a group in a nice quiet laboratory, and we put headset mics on them, and we then process the audio signal to determine whether a student is speaking or not, which is remarkably difficult to do, actually. Silence detection is not that easy. And we look then at the pattern of speaking and silence, and from that plus the actions, we can determine whether or not they're collaborating appropriately according to experts who code the videos themselves. So what we're looking for is the type of collaboration which is sometimes called interaction in the ICAP framework, or transactivity in linguistic frameworks, or co-construction in other frameworks. So it's a very intense, contentful type of collaboration where one person builds upon the other person's comment. They might agree with it, they might disagree with it, but it follows on from it. So that type of collaboration turns out to be highly correlated with learning gains, and that's the kind we want to detect and encourage. But to do that, we need the speech, and to do that, we need the silence detection, and to do that, we need the microphones, which brings us to the cutting edge, which is we now want to try and get mics into the classroom. And the classroom is a very noisy place for that sort of thing. Even with headset mics, the noise generators are other students, and they have the same frequency distribution as your signal, namely the student who's speaking. So it's really difficult to filter out ambient noise. We're still working with acoustic microphones, but now on our next trial, we're going to be using throat microphones. And if those don't work, we're going to use bone microphones. So we're hoping to be able to get speech detection going in the classroom, but we're not there yet, basically because of the noise issue. However, I should have probably mentioned that when we do have the speech in the laboratory, we can do highly accurate discrimination of transaction versus other types of participation.
So you have these detectors that can detect learner activities that require attention. It looks like you're proposing possible misconceptions that might underlie those. Does this go so far as to have sort of a model of the learner's competencies? Is there some sort of learner model underlying this system?
No, we don't have that. But it's not a problem to, once you have done the hard work of analyzing the student's poster and discovered what misconceptions exist on there, and I should mention that we also have detectors for correct work too, then you've sort of found all the instances of good versus bad behavior. It's just a matter of aggregating them in some fashion. In principle, we could just, I mean, we have whole nother project, which is to build a service called CEDAR, which is for student embedded assessment and task recommendation. That takes log files like the ones developed by FACT in real time and runs whatever your favorite aggregation is. It could be Bayesian knowledge tracing. It could be one of the logistic ones. It could be, we're playing around with nearest neighbor stuff, whatever you want. We've got several of them in there. And then it can recommend tasks. We use that in organic chemistry tutoring. So if we were going to develop a student model, we would do it through a service rather than putting into FACT. And different people have different services. CEDAR's not the only one.
So in some of your earlier work, you made reference, you viewed basically sort of intelligent tutoring as kind of a one-on-one activity between the student and the intelligent tutor. In this system, we see much more of a collaboration between the system and the teachers. And I'm wondering, is that just a characteristic of this particular system, or has your thinking evolved in terms of the roles and responsibilities of intelligent learning environments and teachers?
I'd say my thinking has evolved. I don't want to sound disparaging, but I sort of think
Go ahead.
That we did a great job with tutoring individual students, and the technical challenges there are pretty well in hand. We still have instructional design issues, but that's not the forte of engineers like me. That's people who are former teachers and brilliant artists and so forth. That's their job. So we got instructional design issues, but the technical issues are well in hand for individuals, okay? For helping a group become more effective, that's still open territory, and that's been investigated heavily by the CSCL community for a long time. And now some ITS folks are moving into that area too. There's a small movement for what they call CITSs, or KITs, for collaborative intelligent tutoring systems. Stupid phone again. Yeah, that's the leading edge. So I decided to sort of skip over the collaborative intelligent tutoring systems and get right to the orchestration systems, which are the next step beyond collaborative ITSs.
Great. Another question from the audience about FACT. So could you say a bit more about how FACT evaluates student participation when they're in task, out of task, well into task, et cetera?
Yeah, the in-task, off-task thing. Well, if their machine's not responding to the heartbeat, then they're not even running FACT, so that's a simple one. If we've got a doodling detector, it's not reliable yet, but when it gets reliable, that's a form of off-task behavior. But you got to be careful. A little off-task behavior is not a bad thing. So a little doodling is not a bad thing. We particularly see, and we've been studying what we call the collaborative writing process. Excuse me a moment. And the collaborative writing process is such that one student often, they have a discussion, and then one student has to write it down, and the other student has nothing to do. In that case, doodling's okay. So doodling detector has to be much more, how should I say it, contextualized in the whole group activity when it's being used with the group. So yes, we have been studying detecting on-task and off-task behavior, but it's much more complicated than it first seems.
So how do students game this FACT? They're always gaming systems. So what gaming behaviors do you have to deal with?
Oh, absolutely. In fact, one of the cool things that came out of the Lamillo research was they saw very clearly that the teachers were visiting the wrong students, because they would visit the students who appeared to be off task, but the students were very clever about when they sensed the teacher approaching, they would click off whatever they were goofing around with and click back on the right application, and the teachers would think they were on task. yet when you monitor their screens, you can see that kind of thing. So students are good at gaming not only systems, but also teachers. So we see it with, we've upped the stakes by entering, we have a system and a teacher working here, but yeah, they can still game that too. So one of the things we found was very clever. When the teacher is projecting in the group work section, the screen, which shows all the tiles and the students are joining groups, the students discovered they could press the done button and it would cause their tile to turn green. So they had a great time flashing the greens across the room, and the teacher was going, what's going on here? So we had to, we fixed that problem. But yeah, they discover all kinds of holes in the design. They're good at that. They're really good at that.
Great. So I'm afraid we're out of time, but thanks again for a great talk. Thanks everybody for your questions. As a reminder, our upcoming webinars next week, Gautam Biswas is going to be talking about mining and analyzing learner behavior. Next week, he's only going to be able to talk one time next week, so be sure on the 31st, so Halloween. So be sure to sign up for that. And then 2 weeks after that, I'm going to be giving a talk on using data mining and analytics to inform iterative development of instructional systems, if you will, a new paradigm for instructional design that takes advantage of big data and analytics. So I hope you will be participating for those. And for now, signing off. Thank you everyone for participating.
Bye.